Right, shall we, right, here we go. Okay. Kia ora. Look, there's always one. Just happens to be Professor Robert Gourdie. Kia ora koutou, Kosi Brewster, Taka Wingawa. Thank you everybody for coming tonight, and I know that people will be joining us online, so we're really pleased that you have turned out tonight to hear from our amazing two professors again, and they're going to do slightly different topics tonight, which are Professor Donna Rose Addis will be talking to us about the prospective brain in depression, and Professor Robert Gourdie will be sharing about milk nanovesicles. Get that right? Thank you. And the treatment of heart disease and radiation injury. So, but as with last night, I just want to start us off with the same karakia care that we did last night, because it's the one that speaks to about sharing knowledge and having purpose with all that we do. So, e te hui, whaia te mataronga kia marama, kia whai take nai, mahi katoa. Tu maia, tu kaha, araha atu, araha mai, tātou e, a tātou katoa. Kia ora. I'm not going to go through any health and safety. You guys know how to be healthy and safe, and you know where the bathrooms are, so that's all good. But look, this is our final speaker event for tonight. Welcome. For our 70th anniversary, and it's fair to say we have had absolutely phenomenal speakers throughout the series of events we've done. But I think the two more phenomenal are the ones that we have here tonight in terms of their research journey and what they've achieved over the years. So I would really like to thank our 70th partners though, which is the University of Auckland, Shoreham Partners, formerly JMI Wealth, and the Auckland University of Technology for making all of this possible. I would also like to thank the Ted and Molly Carr Medical Travel Fund for bringing these two exceptional professors back to Aotearoa, New Zealand. I think we talked last night about Auckland Medical Research Foundation, but I just wanted to say that really unique thing about us is that our operational expenses are covered by an external benefactor, which we're extremely grateful for. So we're very unique in that every single dollar donated goes directly to medical research, and that is our main mission. So I think what we'll just do is we will go straight into tonight's, what's going to happen tonight. So our first turbocharged presenter tonight is Professor Donna Rose Addis, who I'll introduce very shortly, but Donna Rose will speak for about 45 to 50 minutes, then we'll have time for question and answers, quick 5-minute break, be back here, and then we'll have Professor Robert Gourdie present and wrap up about 8:15, something like that. So, my first introduction of the night is Professor Donna Rose Addis. So, Donna Rose grew up in South Auckland and is the first Samoan neuroscientist in the world, specialising in neuroimaging. And Donna Rose has been living and working in Canada since 2018. In 2016, she was made the youngest ever Fellow of the Royal Society of New Zealand. She's been recognised for her pioneering work in the use of functional brain imaging to study how the brain stores and retrieves memories in healthy people and those suffering from neurological orders. But to tell you about her research, I want to invite Professor Donna Rose Addis to the stage, and please everyone put your hands together and give her a very warm welcome.
Okay. Great, thank you, Sue. Talofa lava. It's so lovely to be here again and to have you all here this evening to be able to tell you about some of the work that we've done on this topic. So I'm just going to jump right in. So in the last 20 years or so, we've seen a real broadening of the conceptualization of memory to consider its role in future thinking. And 2007 was a real watershed year in this idea where we had 3 papers come out from separate labs around the world. None of us knew that other people were working on this on the same topic, and one actually just won a Nobel Prize last year, Demis. So it shows what looking at imagination and the hippocampus can, where that can take you. But what we saw here was three new kind of results that were really taking us in this new direction of thinking about how memory can be used for other functions, particularly imagining the future. And so what we found in our study, when we had people remember past autobiographical memories and imagine novel future experiences, was a striking overlap in activity, primarily in the default mode network. So here you're seeing the medial cortices, when people are remembering the past and imagining the future, as well as subcortical regions such as the hippocampus that you can see here. We also have found parallel declines in memory and future simulation. And so, finding these overlapping neural correlates sort of pushed us in the direction of wanting to see whether we would also see future simulation deficits. And so one of the first studies we did was in healthy aging. And so what you can see here is that to orient you, this is the number of details people are generating in their narratives of past and future events. And looking at younger adults and older adults, we see a reduction in the number of episodic details. So these are the details that are very central to the event that they're thinking about. We see that drops off with healthy aging, and we see an increase in the number of non-episodic details. And just to really drive home this close association between memory and future thinking, we see a very significant correlation in terms of the numbers of past and future details that people are able to generate. And so these lines of evidence led us to propose what we called the constructive episodic simulation hypothesis. And this was really coming from probably a couple of decades of work showing that memory, or episodic memory, is a very constructive process. And we see evidence of this in terms of the memory errors and distortions that people typically have that are very common. And we saw an upside to this fallible nature of memory, that it allows us both flexible access to episodic details. So both when we're remembering and imagining, we're bringing together details to create these simulations. But when we're thinking about future things, novel scenarios, we're having to recombine details into new configurations. And so interestingly, depression is associated with a number of cognitive changes, particularly in the ability to remember the past. And so what we see in individuals with depression is that their autobiographical memories become what is called overgeneral. So they tend to lack specificity, meaning that people don't think of a particular moment in time. They tend to think about maybe routinized or very general scenarios that happen a lot for them. So for instance, they might say, I'm always left out of social situations or something like this. You also see, or we've also found reductions in episodic detail. So even if they are retrieving specific moments in time, the details that they have are reduced. And it's interesting to note that this finding is evident across the spectrum of depression. So we see it in individuals who are suicidal. We also see it in remitted depression, leading some to really think of this as a trait marker rather than a state marker. And we also see it in dysphoria. And there is some evidence that this overgenerality extends to future thinking, or certainly when we came into it, there was a small amount of evidence around this. But what we've done is to really look at what the mechanisms are that underlie these changes in future thinking. So what I'm going to talk about tonight is first to talk about some of the neurocognitive models of how it is that we think about the past and the future, what I refer to as autobiographical thinking. I'll then turn to some of the neuroimaging and related research looking at prospection in major depressive disorder. some new work that we've been doing using text analyses to look at different profiles of autobiographical thought. And I'll end by talking about goal-directed imagination. So first, turning to the models of how it is that we think about our pasts and our futures. So one of the most influential models in our field is the self-memory system by Conway and Plaidel-Pearce. And this is really focused on autobiographical memory, but has been extended to future thinking. And the idea is that our information or our knowledge about ourselves and our lives are stored in this hierarchical system where we have very general or very enduring or long narratives about one's life or about one's major themes in one's life. We can also have lifetime periods that are nested within this life story. So for me, working at Baycrest or my friendship with Genevieve. And then within this, we have different events that become nested. And so these are general events, these kind of categories of things that we may do on a regular basis. So having lunch, at work, going and running MRI scans, working from home on Zoom, various things like that. So these are somewhat generic representations in that they happen often. And then within this, we may have specific examples of, a Zoom meeting that went wrong or going to see a particular movie with a friend. And so you're kind of indexing down into these more and more specific forms of memory. And so we do, many people have mapped this hierarchy to a distinction between episodic memory being the episodes of our lives that have this rich, vivid detail versus more semantic memories that are much more conceptual and factual in nature. And so oftentimes when we're, in our daily lives, we may experience what is known as direct retrieval, where a memory just pops into our mind. And I'll come back to this a little bit later in terms of what's happening here, but I'm want to make a distinction between that and what's called strategic retrieval, where we are actually searching for a memory. And so often or research has actually shown that we tend to start up in these more general categories or levels of memory, and then we search through our memories to find a particular episode that we're looking for. This is important because there's a model of memory of memory dysfunction and depression called the CARFAX model. And what that's really talking about is why it is that we get overgeneral memory due to dysfunctions in this system. And so the first part of this is known as the capture of retrieval. So if you're ruminating and you're having a lot of repetitive but very overgeneral thoughts, you basically take up the capacity of the system in terms of retrieving events, and then you can't actually get into this specific level of specific memories. So here we're trying to explain why it is that individuals with depression tend not to retrieve memories from here, but tend to retrieve memories from here. Another proposed mechanism is functional avoidance. And so this is really an affect regulation mechanism, so that if an individual learns that retrieving very specific episodes from their past is destabilizing or upsetting, they learn to avoid doing that. And so they kind of stay in this level of generality so that they're not kind of, tipping the boat. And then another reason why people may not be able to get from this general event level down into a specific level could be due to executive dysfunction. So when we're trying to retrieve memories, we have to engage a lot of executive capacities, such as working memory, inhibition of things that are irrelevant, and being able to be very fluent and generative and being able to search for information that we need. So I'm just going to come back to that direct retrieval idea here. So when people are encounter some kind of cue in their environment that absolutely maps on to an aspect of a memory, they may be able to pattern complete that memory, so their hippocampus becomes involved and retrieves the rest of the memory. So it's kind of like an autocomplete for memory, and so we think this is that the process that's happening when something just pops into your mind. So you're out and about, you see something, and some really evocative memory just comes back to you. And the hippocampus is critical to this process. So we did a study back in 2012 where we actually compared direct and generative retrieval and found significant activity in the bilateral hippocampus when people have this direct retrieval. But then, as we talked about, sometimes people are having to strategically search. And this is actually, often what is happening in our everyday lives. Someone asks us something, we're trying to think about this. And so we go through an iterative search, retrieval, evaluate cycle where we're trying to refine our cues and find that specific memory. When we actually get there, then we have pattern completion. And so in contrast to direct retrieval, what we first see is lateral prefrontal cortex activity. And so that's what actually allows us to guide this active search looking for this memory. And then once we reach that, then we have pattern completion and we get activation in the hippocampus. And so these are going to be two regions that I'll be talking about today, the hippocampus and the lateral prefrontal cortex. So in depression, the hippocampus is affected. And so we see structural changes, we see atrophy, and this is a very widely replicated finding. A recent meta-analysis put the volume reductions at around 8%, but this can range from 4 to 10%. And so you can see in this sagittal section here, a control hippocampus and a hippocampus with somebody who's had multiple episodes of depression. And so there's been a lot of atrophy here. And this is related to the neurotoxic effects of stress. And that includes a suppression of hippocampal neurogenesis. So you're actually seeing increased atrophy related to this process. And interestingly, it seems to be the dentate gyrus in particular that gets affected. So those of you who were here last night, I was talking about a hippocampal amnesic that has very selective damage in the dentate gyrus. And so here we're seeing, it's hard to see, but there's this kind of light aqua color. That region is somewhat reduced in this person with major depressive disorder relative to a healthy control. Hippocampal atrophy has been found to be a marker of risk of developing major depressive disorder. So it's evident in young adults who have a family history of depression, so who are at genetic risk of developing depression, as well as at the onset of the first episode. It's also associated with early life stress, and a lot of work has looked at childhood abuse and maltreatment, and finding significant changes in the hippocampus. And it's also a marker of disease state. So as I mentioned before, the more depression you experience over your life, the greater the level of hippocampal atrophy. And so those who have an earlier age of onset, it correlates also with the severity and duration. And so here's a measure of severity of depression symptoms, and we see an increase in that level of atrophy, estimated atrophy in these individuals. And so I bring you back now to our findings around past and future thinking. So now to try and connect this back around. So we did see a lot of overlap, but we also saw differences between past and future thinking. And this is important in terms of thinking about whether the future might be more affected in people with depression than memory. And so we saw differences in particular in the hippocampus, in the anterior aspects. where this region was more activated for future thinking than for remembering. And we've done a lot of work that's shown that imagining the future is certainly more cognitively demanding than remembering. You're having to generate something new from scratch, and so there's a lot of cognitive effort that goes into that. And one of the things we think that is really important is that unlike when you remember, when you're putting back details into the place where they've already been associated together, when we imagine, we're recombining details to form something novel. And so Rhys Roberts, who's here, has done some work taking all of our, 7 of our imaging studies over the last few years and doing what's called a mega-analysis. And so here, just to orient you, we're looking face on at the brain, and this is this is the anterior portion heading backwards, and this is the hippocampi sitting in here. So this is the very anterior part of the hippocampus. And of course, this is the outside of the head into the medial aspect. And so what Rhys found here was that there were particular regions in the hippocampus that are significantly correlated with the amount of detail people are able to imagine when they're thinking about the future. And so this was done on a trial-by-trial level, which is really important. So rather than just saying, oh, let's do a correlation of people who imagine things really vividly and those who don't, everybody has a different performance trial to trial. And so Rhys has captured this in this analysis. And so any time that somebody's imagining something with more detail, the hippocampal signal ramps up. And so it's really tracking with that level of detail that people are imagining. And it's of interest to us that this is in the anterior hippocampus. It really replicates some interesting other findings in the literature. Another region that in our original 2007 study that we found was more active when people were imagining was the lateral prefrontal cortex, particularly the inferior frontal gyrus. And so this is the same region that we're seeing here when people are engaging in that strategic form of retrieval, when they're engaging in a search process. And we think that when people are imagining, you're having to engage that kind of strategic process in order to generate something new, but also to find relevant bits of information to put into your novel imagination. So you are engaging in aspects of retrieval to find information. And interestingly, the same region shows changes in, or structural changes in major depressive disorder. And so this is from a study looking at cortical thickness. So that led us then to want to look at the prospective brain in major depressive disorder and see what actually is happening when individuals are trying to remember and imagine in depression. And so I mentioned there'd been a little bit of evidence that there were some deficits in future thinking. There was this very seminal study by Williams and Broadbent back in the 80s, and this was with suicidally depressed individuals. And so they're being asked to remember experiences in relation to positive, negative, or neutral cues, or to imagine experiences, again, positive, negative, neutral. And in all of these conditions, you can see that those who are suicidally depressed are generating far fewer specific events than those who are healthy controls. And interestingly, though, there have been contradictory findings since then. So there'd been a few studies that had looked at future thinking in depression, but the findings were mixed. And yeah, this was the interesting point I was going to make, was actually that even though they collected past and future events, they did not compare the rates of specificity between these groups. So there was no statistical contrast of this, and they didn't consider other aspects or factors that could be involved, like hippocampal atrophy or strategic retrieval processes. So Williams went on to propose that Carfax model, and it's very much focused on psychological mechanisms of rumination and avoidance. So one of my PhD students, Bo Gamble, started his PhD by doing a meta-analysis of all the studies of future thinking in depression. And when looking across a very broad range of studies that took into account people with dysphoria right through to suicidal depression, he had 4,800, or data that came from 4,800 individuals, and found a small but reliable deficit in future thinking. And so this is taking into account any kind of paradigm people are using, any kind of stimuli that they're using, so it could be positive cues, negative cues, or just neutral cues. So all of these things are embedded in this analysis, and we still get it's a small effect, but it's certainly there. These are the studies in individuals with suicidal depression. So of course, a very extreme result there. But what was really interesting was that he found that valence was a really important aspect of this. So for individuals with depression, when they're asked to imagine positive future events, this becomes very difficult for them. And so you can see here the effect is very strong when we're looking at studies that had a positive affect condition. And this is an interesting contrast from anxiety, where the negative future becomes almost too present and too easy to imagine. So here in depression, we're seeing this difficulty with imagining a positive future. So then we wanted to look at different mechanisms that might be involved in this, looking at things like hippocampal function, the psychological versus the neurocognitive factors that might be involved, and seeing whether there's a difference between future and past. So now we've sort of established there's certainly a mild deficit in depression for future thinking. Is this more than what we see for people's difficulties with remembering? And we wanted to look at this too in a wider range of depression rather than just very severely depressed individuals. So a former postdoc, Sylvia Hack, and Chris Murray, a former clinical PhD student, undertook this research. And so for the fMRI study, or actually for both of these studies, we had individuals who not only were currently depressed, they could also be enrolled in the study if they had a previous diagnosis of depression, but weren't currently depressed. So this was really going with the idea that people can be showing these changes even when their depression is in remission. We had individuals who were fairly young, but they ranged in age from 18 to 45. And what I want to point out here is the BDI-2 was our measure of depression, and so as a group, our depression group were significantly more depressed at the time of testing, and more anxious, actually. And so then when they were in the fMRI scanner, we gave them a task that's very similar to what we usually do in these kinds of studies. So we gave them cues that instruct them to think about the past or imagine the future or to do a control task. And then we give them some kind of cue to help them, give them somewhere to start. What's different in this study relative to our previous work, and actually relative to much of the behavioral work in the literature, is that instead of giving them a single cue word, which is often what is done, we gave them an event type. So something that actually relates to an event. And so these, we called them supportive event cues. And the reason why we're doing this is because when you're looking at patients in functional imaging, you want your patients to be able to do the task that you're interested in. So if you put people into the scanner, so my PhD supervisor always said, if you put an amnesic person into the scanner and you ask them to remember something, what are you actually measuring in terms of what their brain is doing when they cannot remember anything? So you want them to be able to actually do the task. So in this case, in all of our imaging studies, we only analyze events where somebody successfully remembers something, an episodic memory, or they successfully imagine an episodic event. So we have people do a post-scan interview afterwards. They tell us what they were thinking about in the scanner, and if they come up with a particular event, that trial will get put in the analysis. If they come up with something that's a very routine or a repeated type of event, then we don't analyze that. So that we can be sure that what we're looking at are the neural correlates of actually doing the task. And so by using these supportive event cues, we generally boosted people's performance, and so that gave us enough trials to be able to do these analyses. And so what we found was that overall, there's a lot of regions that are commonly activated between the depression group and the control group when they're doing these tasks, and of course they are successfully doing the tasks. So you can see in some of these regions, like the left medial prefrontal cortex and the left middle temporal gyrus, there's nice activation during the autobiographical tasks in the warm colours versus the control task, and we're seeing that in both groups. But there are some differences, and one of these is reduced activity, and I'll get onto the connectivity in a second, but reduced activity in this area of the right, fairly anterior region of the hippocampus. So this really fits nicely with Reese's mega-analysis showing the right anterior hippocampus. And so while there is a difference here in controls that's significant, the difference is much reduced in people with depression and no longer significant. And so what we wanted to also look at in this study was connectivity. So how is the hippocampus interacting with other regions in the brain while doing these tasks? And so we took activity from two regions, left and right hippocampus, and we found a network of regions that associated or were correlated in their activity with the left hippocampus and one with the right hippocampus. And there are many of these same regions that we typically see engaged when people are doing these kinds of tasks. But what's interesting here is that the strength of connectivity differed between the groups. So for future thinking, the connectivity is around 0.83 in controls, and it's around half of that in people with depression. And that difference is significant, and it's about the same here for past events. So people with depression are showing this pattern of connectivity, but it is just much weaker. Interestingly, the depression group showed activity with connectivity with other regions that the control groups do not. And so here, during the past condition, we see it's and this only was evident for the right hippocampus, that the patients or people with depression were engaging or showing connectivity with regions of that default mode network. So lateral temporal cortex, inferior parietal cortex, precuneus, and they're showing this additional connectivity in a way that the controls are just not showing that at all. And this is what's really interesting to us, is that when they imagine the future, they engage an entirely new network. So this is what we would talk about as compensation. So individuals here with depression are recruiting the attention network to help them do these tasks. So when they are able to do it successfully, they're pulling online another network. So then we also did a behavioural study with these participants, and we expanded our sample somewhat. So we have 8 more people in each group. And with these individuals, we did both psychological and neuropsychological measures. So here what we were trying to do was test out these different hypothesized mechanisms. And so one of them, as I'd mentioned before, was rumination, that maybe you kind of fill up your capacity and you can't think of or can't remember specific things. One was about avoidance, so are you avoiding retrieving certain kinds of memories? And then one looking at different kinds of executive functions. And the one that we were most interested in, and that no one had really tested out, was strategy use. So people's ability to strategically retrieve information, and we think that that is, it's a function of that lateral prefrontal region that we've seen, and was something that was of great interest to us. And so in these participants, when we look at their performance on doing our past and future tasks, we found that the depression group generated fewer specific future events. So they don't show a difference from controls for past events. And we think this could be because of, we're giving them these supportive cues, and that was enough to boost them up into the performance range of healthy controls. However, that wasn't enough for future events. So it really does speak to this idea that it is more cognitively distinct. We took the transcripts, and then the transcripts of the memories that people generated and their future events, and scored them for the types of details that they generated. And so we found that even when we only looked at specific events, so an event that refers to a memory or future simulation that refers to an event that's specific in time and place, so a particular moment, we see a drop-off. It's very small, but a drop-off in episodic details and an increase in non-episodic details. And so that was a very interesting finding to us as well. In terms of looking at these different mechanistic processes, we found a group difference in terms of avoidance. So depressed individuals scored higher in terms of their avoidance and higher in terms of their rumination. But there was this difference in clustering ability, which is our strategic retrieval measure, was not significantly different, although you can see it is lower. But when we looked at correlations with the ability to generate specific past and future events, this clustering measure did correlate with that. So these were our three measures then that we then took into our next set of analyses, where we looked at regressions in the depression group to see what would be predictive of their ability to generate specific events. And so for past events, we found we did not get a significant regression model, so none of these predictors were informative. But for future event specificity, we got a significant model, and it was the clustering, the strategic retrieval measure, that really predicted the ability of people to generate specific future events. And what's really exciting about this work is that now it's been used to develop a new intervention for depression. This is from David Hallford in Melbourne and some other colleagues around the world, where they've developed a guided training therapy to basically a phased training to teach people how to simulate positive events. And it's designed to increase the specificity of those events, the vividness and mental imagery that they're using, and also to enhance anticipatory emotions. So really to get people thinking about what is the anticipated pleasure that I might get out of this event, and really allowing them to engage in this. And they found that this not only does this improve your future thinking abilities, but it reduced the likelihood of anhedonia in these individuals, and then reduced the number of people who were actually in an episode. So there's a lot of promise for this kind of technique, and so it's really great to kind of see others taking some of this work and taking it through to that translation. So another thing that we've, this was something that the pandemic forced upon us, was to take our research in a new direction to look more at text and natural language processing. So because I'm based at a geriatric hospital, we couldn't test in person for about 2.5 years, so I certainly wasn't scanning anybody during that time. But what we could do was collect narratives from people online. And so we were interested in looking at more unconstrained forms of autobiographical thinking. So all the tasks I've shown you so far, they're very experimentally controlled. Now we just wanted to see, well, what do people do when we don't give them any instructions about how to think about the past or the future? And so the sentence completion task, you give people sentence stems and then they can finish them in however they like. And so that allows us then to kind of gather a lot of autobiographical thoughts from people. So we did this in a fairly large sample for our kind of research. So we had 203 people who completed all of our trials, aged 18 to 74, about 50-50 in terms of sex, and a range of education as well, which is really nice to see, because oftentimes we end up with mainly university students in our studies. And so we also had a range of depressive symptoms. So 52% reported on the patient health questionnaire, no current depressive symptoms, whereas the other 50% ranged in terms of their degree of severity. And we actually went through and we hand-coded the specificity of all 3,654 events, myself included in some of that. And so I guess when you're locked down, there's not a lot else to do except code people's thoughts. So we did a lot of that. And what we saw, which reflects what we expected to see, is that specificity is higher for the past, so it is easier to remember past events, and so people tend to generate thoughts that are higher in specificity. So this is the mean proportion score that people got. And so on average, the proportion of people's thoughts for the future that were specific was about a third. So then we used a technique known as the linguistic inquiry word count technique, which has many variables. It's basically a dictionary method that allows you to go through and get all sorts of different features of the text, as well as counts of words in many different categories. We also created a custom dictionary for the pandemic. And from this, we basically, for every single thought, we get 93 variables that tells us something about what that thought contains in terms of its content. We then, in what was more of a novel direction, so I should say people have been using this for quite a while, where they would say, oh, people with depression have fewer, negative words and more positive words, and then that was kind of about it. So what we did was we submitted it, all 93 variables for all of those 3,600 narratives, to principal components analysis, and that pulled out these different components here. We did it for past and future separately, but interestingly, the patterns we got for past and future were very, very highly correlated for 3 of these, and then 2 of them are not so correlated. And I'll show you what they actually reflect. So when we looked at these patterns, one is coding for episodic richness of past and future events. One is related to self-focus, so it's a lot of words around internal, when you turn your attention inwards to your emotions, to your thoughts, your feelings. One is about positivity. One is about the negative past, and one is about goal-directed future. And so then we could take these profiles, the degree to which a particular person expressed this thought profile, and see whether particular characteristics of that person might predict their thoughts. And so we looked at depression scores and specificity scores, because that's what we're very much interested in. We also had age in there as well, because we had such a range of age. We had to control for that. And we did have some interesting findings with respect to age. I'm just not going to talk about them tonight. But we found that higher depression and having lower specificity, or having more general thoughts, was associated with an increased self-focus. So that seems very reflective of rumination, thinking about very overgeneral things that are very kind of inwardly turned. In terms of positivity, we also found this to be significant, this positivity profile here. So that individuals that have very specific responses and they had lower depression tended to be talking about positive information. People with higher depression, who were very specific, were talking about negative information. And that in of itself is a very interesting finding because it goes against the idea of overgeneral memory being how people with depression, do memory and do future thinking. And so there is actually Karen Salmon at University of Wellington, Victoria in Wellington. She has also found similar findings where adolescents with depression show more specific future thinking, and in her case it's around very self-defining events. And so it seems in this case it was a lot to do with the pandemic. And so individuals with depression seem to be very fixated on the negative details about the pandemic and couldn't seem to kind of get past this. So I think that's a really interesting finding that's kind of putting a bit more nuance back into the literature now that people are using other paradigms and other ways of looking at autobiographical thinking, not just the one task that's been used for the majority of the research. Okay, so I'm just going to end up now talking about goal-directed imagination and well-being. So goal pursuit is a big reason why people think about the future, and it's actually also crucial for our subjective well-being. And it's aided by us being able to simulate future scenarios that help us get towards those goals. And so when Bo came into my lab, he was really interested in wanting to run a really large study for our type of research, where he looked at individual differences in goal-directed simulation and to see how this was related to both well-being and depression, so to look at both sides of that coin. And so he recruited people aged 18 to 50. They were around 2/3 of them were women. And in his study, he had people generate lists of short-term, medium-term, and long-term goals. And then they had to pick their 6 most important goals, so 2 in each of these categories. And for each of those, they had to imagine a scenario related to that goal. And then he collected a whole lot of variables, so different ratings that they had to make to characterize both the simulation that they created and the goal that they were thinking about. And it looks something like this. So these are all the different variables that he collected around the simulation quality and the content. And he found that many of these were associated with well-being and on the other side with depression. And so what we can see in terms of clarity, so the degree to which people could think really clearly about their future goal and their simulation, how detailed that simulation was, how vivid it was significantly related to well-being. On the other side, if it was not clear and not vivid and rather was fragmented, then you saw an increase. This was associated with an increase in depression. In terms of looking at what people were, whether they were focusing on the process or the steps to the goal versus the outcome of the goal. For those people who focused on the process, they were less depressed. And then in terms of negativity, as you might expect, those who thought about negative things had lower well-being and higher depression, and vice versa for positivity. What's important here is that actually we found that negativity predicted people's well-being at a 2-month follow-up. So it wasn't just in a correlation that we happened to have at that time. He got people to come back in and tested them 6 months later, and 2 months later, and was able to show that this negativity at this time point was actually related to lower well-being at that follow-up. And then in terms of the goals that we choose for ourselves is also, that's also an important thing. And so if we choose goals that are attainable, we're going to have people showed higher well-being, a higher sense of control, and the opposite pattern for depression. Goals that are important to us, that are central to our sense of self, and that we expect will bring us joy are associated with well-being. And then things that we feel that we have control over are really important as well. And so particularly with respect to depression. So if we feel like things are outside of our control, and this affects a number of life domains, then there's a higher likelihood of depression. And so the attainability of these goals actually predicted people's goal process at their progress towards meeting these goals at the 2-month follow-up. So this is, a really nice way of looking at a much more, getting a range of results that give us some practical clues here about things that we can do to help people with their well-being and their depression. But we're actually also using this now in terms of dementia prevention and thinking about, okay, can we do goal-directed simulation to help people in terms of their adherence to particular programs or goals that they set to reduce their risk of dementia. So that's something now that we're also doing. Okay, so just to conclude then, there are certainly changes to future thinking in depression. It seems to be less specific, and this is related to structural and functional changes in the hippocampus and the lateral prefrontal cortex that affect both strategic retrieval processes as well as being able to generate detailed and specific future events. But on the other side, we see recruitment of additional brain networks in those with depression to help them do these tasks. Major depressive disorder is associated with altered thought profiles. So we have evidence now from people's narratives that there's an increased self-focus as well as very specific but negative future thoughts. And that goal-directed future thinking is an important aspect of our well-being and perhaps as a way to offset depression, if we can vividly imagine attainable goals that are central to our sense of identity, that these are things that are really important for our well-being, and that simulation is a pathway to perhaps reducing the hopelessness that's associated with depression and creating for ourselves a brighter future. So I just want to thank all the people that have helped with this research program. So Lynette Tippett and Reese Roberts, who are both in the psychology department at the University of Auckland and have collaborated with me for a long time. Reese, it's 16 years now. Bo Gamble, Sylvia Hack, Chris Murray, who did all the work, the studies on depression that we did here at the University of Auckland, and then Ria Tricker and Sam Fine-Clintons, who helped me do all the thought profile work in Toronto. And to all my sources of funding, and the Te Mori Car Medical Travel Fund for bringing both me and Rob here to help celebrate with AMRF for their 70th anniversary. So thanks so much.
Fantastic, as always. Thank you very much, Donna Rose. And so now we know that what you did over COVID, you coded nearly 3,500 thoughts.
Yeah.
It's a lot.
Yeah.
So Hannah's just grabbed the roving mic. So if there's any questions that you've got for Donna Rose, please feel free to fire. Oh, Reese has got one. Even after 16 years, he's still got a question.
Can you hear me okay?
Yeah.
So you showed a slide that the densate gyrus might have specifically show atrophy, and there's the densate gyrus is associated with pattern separation often.
Yeah.
So I thought I had was something like, well, maybe this lack of specificity is happening at encoding because people with depression can't engage in pattern separation, so very similar events just kind of all meld into one thing. And so I just wondered, I don't know, have people looked at this?
I
Depression.
I don't think there's been a lot done on this. And I think certainly with respect to autobiographical memory, people have never looked at encoding. And, one of the reasons is because that's so challenging, right? Like, how do you look at, people encoding their memories on an everyday, basis and then be able to study that? And one of the things that I would like to do but haven't done yet is to do one of these, constructed experience type studies. So we actually have one at Baycrest Hospital where I work, where there's actually a museum tour in the hospital. And so you can get people doing this tour, and then you can then test their memory for that tour. So that might be something that, that would be a really great thing that I would love to do. So I think that's definitely something that has to be done. But even maybe looking at pattern separation tasks too.
Yeah, but there are these new kind of cool, kind of ecologically more valid things of videos of routes that are intersecting, and really similar routes produce this pattern separation effect. And
yeah, that sounds
controls,
interesting.
And it'll be, anyway, just an idea.
Yeah, cool. Thanks.
Fantastic talk, Donna.
Thank you.
So I have a couple of questions. They're kind of related. I picked up that the vividness of future thinking may be helpful in ameliorating depressive symptoms.
Yeah.
So is that also to say that vividly remembering positive past events doesn't have a similar effect? And then the second question is, could vivid future thinking be used to intervene for other pathologies like addictive behaviours, etc.?
Yeah, that's a really interesting question. So I think that particularly in depression, there seems to be this feature where future thinking seems to relate to a lot of symptoms like hopelessness and the sort of future directed, there's kind of some sort of future directedness in terms of what's going on in terms of people's clinical symptoms. And so that could be why then, the vividness of future thinking or lack thereof then has such an impact for people in terms of, even behavioral activation. So being able to, get out of bed and, kind of offset these motivational symptoms as well that are happening. Remembering the past, maybe that's in a positive way, that can be good. And maybe, we do that a lot to reminisce and for social things, but perhaps it's this kind of future-directed thinking that is more important in terms of like getting you up and getting you motivated. And relatedly then, thinking about using future thinking to offset other kinds of pathologies. So there is work, and you mentioned one of your colleagues who does delay discounting research. And so this idea that like if you're willing to, some people are going to be much more impulsive and want to take a bigger reward now, and other people are able to, let that impulse go and delay gratification and wait for some better outcome later. And so we're always faced with these kinds of decisions that we're having to make. And so one thing that's actually been used quite successfully is to use future thinking or future simulation as a way to get people to connect with their future self, and so then to make decisions that are better for their future self. So to not necessarily choose the, less advantageous outcome that's, right in front of you, and be able to kind of delay gratification. And they've done this now. There's a person in Buffalo, Epstein, and colleagues who've done a lot of work looking at this in different public health behaviours. So looking at overeating, smoking cessation, gambling, and we also looked at this during the pandemic with respect to vaccination and public health behaviours. And so people who were more impulsive in their decision-making on delay discounting tasks were also less likely to be vaccinated. And we showed that in a multinational sample. And so now we've been, since then, doing work looking at future simulation and getting people to think around, different scenarios and seeing whether that changes their behaviours in terms of choosing these health behaviours.
Thank you, Donna Rose. Welcome home.
Thank you.
I was interested in your the memory retrieval and the overgeneralization of the retrieved memories of depressed individuals. From a methodological perspective, do people kind of cross-check the overgeneralization in terms of maybe interviewing a partner or family and friends? To see like how overgeneralized or how wrong the memory is, and at what point then does this tip over to, I guess, depressed people imagining false things?
Yep. Yeah, that's a very interesting point. So it used to be a big debate in autobiographical memory research about how could you really trust people's memories, and you had to be able to validate everybody's memories. And so we used to, 20 years ago, invest in these very expensive studies or very time costly studies where we would go and interview family members and validate every memory that the person was retrieving. And then at some point we realized that actually, well, certainly in terms of brain imaging, the brain will, still be reactivating in many of the same ways if the person believes that to be their experience. And so in an everyday situation, when a person with depression is remembering this, they believe that to be an accurate reflection of their past. However, you raise an interesting point in that people's retrieval can be biased by various factors, and depression could be one of those. And another one that biases the way in which we retrieve things or imagine things is our schema that we hold for about how we understand the world to work. And so that's actually something that we've started looking at now in our lab more generally, is to look at the role of schema in imagination. And so how you use your past experience or your knowledge of how the world works as a framework for imagination. And so we recently wrote a paper where we argued that, if individuals with depression have negative schema, if that is how the world is for them, then to imagine something that's entirely different from how you understand the world to work is actually really cognitively demanding, even more so than, and we're asking, these are people that also then have executive dysfunction as well. So it just becomes maybe an insurmountable task. And so that's why I think some of these therapies that are kind of guiding people through the process of how to do this and how to create positive imagined futures for themselves could be really useful. Thank you. Right. Thank you so much.
Yeah, well, thank you very much, Professor Donna Rose Addis, and I'd just like us all to give another round of applause for our appreciation. Thank you. So by my watch, or by the clock up there, it's just past 7:05, so if we're back here 5 minutes sharp, we'll kick off for the next session.
Okay.
All right. Good skills.
Let's need to change the batteries actually. I need to put some fresh batteries in.
All right. Fair enough.
Probably a minute.
Okay.
Oh, yeah. 2, 3, 1, 2, 3, 3. I'll put it a little bit higher up. There we go. 1, 2, 3. Is it working?
Batteries.
All right.
All right, kia ora. Here we are for the second part of the evening, and our second equally turbocharged presenter is Professor Robert Gourdie, a New Zealand educated scientist and internationally acclaimed cell biologist specialising in cardiovascular and biotech innovations. Robert has worked in the United States since the late 1980s, and his research spans from fundamental cell biology to therapies moving towards the clinic. So Robert completed his undergraduate and graduate studies in Aotearoa, New Zealand, before doing his postdoctoral research at the University College London. He is the Hayward Fralin Professor at Virginia Tech and Director of the Centre for Vascular and Heart Research at the Fralin Biomedical Research Institute at Virginia Tech. He also co-funded Zequel Bio Inc. and is the founder of the Tiny Cargo Company. But let's hear from Professor Robert Gourdie himself about his fascinating research and career.
All right. Thank you. All right, thank you, Sue, and thanks to the AMRF and also the Ted and Molly Carr for paying for the travel that got Donna and I here. And also I want to thank my neuroscientist colleagues for hanging out. I'm going to talk about the heart, I guess. So I tried to add a little bit of neuroscience in last night, right at the end there. So anyway, but I have props. I've got to get one prop out. Some actual milk, as well as a glass from the hotel. And I'm warning you, there'll be a clinical trial in this lecture. Okay, do I have the advances somewhere?
It's just on the table.
Oh yes, okay, excellent. All right, so I'm going to talk about milk exosomes, these tiny nanovesicles produced by all the cells in our body, but just a little bit of introduction first about how I got there. So it's ironic, but as a youngster, a teenager, I spent a number of years working on dairy farms to earn a little bit of extra money during the holiday break. And so, so I'm familiar with the scene here. I joked the other night that it still makes me a little bit glum when I hear the sound of a milking machine come on, maybe on a TV show or even maybe I'm on a farm. Because it sort of takes me back there and I think it's 4 a.m. I've got to get up. The darn cows need milking. All right, so this is the Fralin Biomedical Research Institute of Virginia Tech. It's located in Roanoke, which is about 30 kilometres away from the main campus in Blacksburg. Virginia Tech's an institution of around 40,000 students. It has very strong engineering and agricultural programs, as well as a veterinary school. And the medical campus was really only established 15 years ago. And so I was recruited there to help by my boss, Mike Friedlander, to help lead the cardiovascular effort there. In this talk, I do have some conflicts. And so here are some disclosures of companies that I founded or co-founded. And I just want to say a word of thanks to my lab. They're a group of dedicated and remarkable individuals, and of course they do the work. My main job apparently is to beg for money, which I spend a lot of my time doing. But this is a great group of people, and as I say, I really enjoy working with them. All right, so this is a curve. These are curves of mortality in the US, and the main point of this is just to demonstrate the principal causes, which turn out to be heart disease, cancer, and stroke. You can see there's a little bit of a blip here with the COVID that occurred back in 2020. But by far, the dominant causes of mortality result from heart disease, cancer, and stroke. So just to put some actual numbers on it, about over 500,000 people in the US die from either heart disease or cancer, and over 150,000 from stroke. So together they account for about 1.5 million lives lost per year. And in New Zealand, the equivalent numbers are around 10,000 each for heart disease and cancer, and 3,000 people for stroke. So in this talk, I'm going to talk about how my journey into basic cell biology led me to start thinking about ways to approach the treatment of these diseases based on the kind of cell biology that we were engaged in. So here is an animation of the heartbeat. This is my little joke here. The heart is an electric organ. It's kind of not, though. It's more like a drum than an organ. But nonetheless, here it is beating away with the activation being spread from the atrial chambers into the ventricular chambers. And via this pumping action, of course, electrical activation gets converted into mechanical pump action. And of course, it can go wrong. This represents a cartoon of atrial arrhythmia where the small chambers of the heart, the atria, are quivering. Often people think of this as somewhat benign, although it can be very distressing. But actually, it can be deadly because around 20% of stroke deaths result from atrial fibrillation. What happens is blood clots form within the interstices of the atria, which then migrate into the brain and can cause blood clots. So my work largely focuses on communication between cells. And one of the main direct methods that cells use to communicate are these channels here called gap junctions. And so basically what happens is that information, small molecules of less than 1,000 Daltons or so, can be transferred directly from the inside of one cell via a narrow conduit into the inside of the cytoplasm of the neighboring cell. And so we can think of gap junctions as a way of enabling direct and rapid sharing of signals. A metaphor that I use is that they're kind of like the tissue's internet. Now, here's another cartoon representation of the gap junction. Here is a membrane of one cell, here's the membrane of the other cell, and what you can see is a cluster of channels made up of a half channel contributed in the membrane of one cell, docked with a half channel from the neighboring cell. And in the cutaway view, you can see that it forms this conduit linking the two cytoplasms together. Now, I actually haven't worked much on the gap junction per se. I have focused in particular on this region at the edge of the gap junction, a region that we gave the name the perinexus. And what you can see depicted here is an undocked half channel or hemichannel waiting on the edge of the gap junction in this perinexus. And over work of the last 20 years or so, we've shown that the way this works is that these half channels are scaffolded in place by interactions with proteins, such as this protein here, ZO1, which links the half channel to the actin cytoskeleton. And this acts as a brake from the hemichannel from migrating into the gap junction proper and then docking with a channel from the neighboring cell. We published a series of publications on this over the years. And I'll also give credit to my wonderful graduate student, Matt Redd. He and I co-named the perinexus in this paper here in Molecular Biology of the Cell back in 2011. This is an immunolabeling of a gap junction. So the way to imagine it is here in this green fluorescent signal, we have the gap junction cluster as represented here. And then around the gap junction cluster, we've got this beautiful halo of ZO1, which is holding these hemichannels in place. And so, as I say, the principal role of the ZO1 is as a brake on the hemichannels joining the gap junction proper. So this perinexus really, as the title says, sealed my fate. So for the next 15 years, this is what we worked on. And last night I talked about the role of the perinexus in cardiac bioelectricity. And at this point, I'm going to use my first prop. This is a couple of plates from the hotel that I took. This is the gap junctional membrane of one cell and the gap junctional membrane of the other cell. And so the way to imagine it is that the cleft of the perinexus is, of course, where these two membranes come apart. And it's that specialised domain of extracellular space that's formed in that cleft. I'm almost afraid I want to point, but I don't want to let go of the second plate. It's in there where the business happens. All right. I should have drawn some channels on them. I didn't have a marker pen, though. I'm not going to talk about that tonight, though. I'm going to talk about some of the constituents of the perinexus, in particular the connexin 43 molecule itself, which make up the subunits of the gap junction channels, and its relationship to ZO1 in injuries of the heart and other organs. So here's a depiction of this subunit molecule. You notice that each of the gap junction half channels were made up of 6 subunits in the previous slides. Well, here's one of them. You can see it's folded in the membrane, crossing it 4 times. But the domain that we're mostly interested in is the C-terminal domain here. C-terminus means carboxyl terminus, of course. This sequence of amino acids here is the actual ZO1 binding domain. And so one of the things that we did was we generated synthetic peptides based on the C-terminal sequence as a tool to disrupt the interaction between ZO1 and connexin 43. The first of these peptides we generated was we linked the ZO1 binding domain. You can see it has the sequence RP, DDLEI, to an antennapedia cell penetration sequence. And the reason we did that is, of course, the ZO1 interaction occurs in the cytoplasm, so we needed to get the peptide across the membrane so it could get to its target. We subsequently found that the shorter sequence also had bioactivity, and I'll get to that in a minute. So the point, though, to make or to emphasize is that originally we developed these peptides for very cell biological questions. Like, for example, if we took away the ZO1 break, did the gap junctions get bigger? They did. Does it change the position of where the gap junctions occur between the cells? It does not. It seems largely to be associated with the aggregation of the channels. Now, this is my old boss, Colin Green. Colin was at University College when I went to do my postdoc there with him and Nick Severs. And of course, he eventually came back to the University of Auckland in the ophthalmology department. But Colin had published a paper showing that if you knock down connexin 43 using connexin 43 antisense, the rate at which skin wounds in mice healed accelerated. And so we got interested in this. And I had a young, newly minted PhD who also had a veterinary science degree, Gautam Gatnikar, join my lab. And what we started doing was asking the question, could these peptides have a similar effect to what Colin was seeing with the antisense? And so what we initiated it first with doing scratch wounds on monolayers of cells and measuring the rate at which the scratch wounds closed, and found that this peptide, we call it alpha-CT1 again, increased the rate of closure of these fibroblasts in a dose-dependent manner. And then similarly, in small skin wounds on mice, this is a 5 millimeter circular excisional wound, we saw an acceleration of the rate at which the skin wounds healed, and also reductions in inflammation and a modest reduction in the level of scar tissue. At about this point, Gautam actually left my lab because he wanted to start a biotech company based on these results. I helped him with the clinical testing of the peptide, not so much on the clinical trial side, but nonetheless, we spent a lot of time talking about design, etc. But he went on to lead 3 clinical trials looking at the effect of alpha-CT1 on, what have we got here? Chronic venous leg ulcers, diabetic foot ulcers, and also whether the peptide could affect scarring from small surgical wounds, such as laparoscopic incisions in the abdomen. And each of these 3 trials returned positive endpoints. accelerating the healings of these 2 chronic wounds, and also modestly reducing the level of scarring in the patients receiving the laparoscopic incisions. And in fact, I had one of my biomedical engineering students went on to look at the potential mechanism of the effect on scarring. We had some tissue from a phase 1 clinical trial that Gourdie had performed. And what we noticed was that when we resampled the scar tissue that had healed into the scars, the collagen organisation very much more resembled that of unwounded skin than the scar of the untreated wounds, which tended to have a much more sort of linear, uniform organisation. And this was really the only variable that we could find in these scars that was associated with the improvement in scarring in this trial. So the company we initially formed was called First String Research. It was bought by a private equity group in California, and they decided to rename it Sequel Bio, and they closed on a deal with a pharmaceutical company this year, which is nice for the company. I have to say I haven't seen any money from this deal myself, so that's a bit of a little bit sad. But nonetheless, the money is going towards the ongoing clinical testing of the alpha-CT1 peptide. All right, now the clinical trials I've just talked about, the peptide is put directly on the skin wounds, and so that means it's a topical agent. But we started to develop some data from research that we were doing that the peptide might also be helpful for other types of injury, in particular injuries to internal organs such as ischemia reperfusion injuries that occur during myocardial infarction. And so this is Jenny Jiang. Jenny did a PhD with me. She's now back in China, where she continued her clinical career, doing a little bit of research along the way. But she did a very nice study, and she's got fantastic hands. And the model she used was a mouse heart that we extracted from the animal and kept beating by perfusion with oxygenated Krebs solution. She also placed a tiny plastic bag about the size of a matchstick head inside the left ventricle of the mouse heart so that she could, with a pressure transducer attached, so she could measure the contraction of the heart. And we used this contractility as a proxy for the healthiness of the heart. This purple block here is actually compressed together oscillations of contraction. And you can see prior to the injury, the heart is beating quite nicely. And it's during this period that we perfuse in our peptide for about 20 minutes. Then the hearts were subjected to no-flow ischemia. So the flow of oxygenated Krebs was stopped, as you can see here, and the beating stopped. And then we started the flow again after the 20-minute period was over. So in the control hearts, what you'll notice is that the hearts do start to beat again, but the height or the amplitude of the beating is much lower in the control hearts compared to those hearts that had received the alpha-CT1 peptide. Now, this is what we call an ex vivo preparation, and of course we can add our drugs and so on to the perfusion solution. It's not completely analogous to an in vivo situation, even though we're looking at an injury to an internal organ. But nonetheless, we concluded that this provided evidence that these connexin 43 C-terminal mimetic peptides, like alpha-CT1, protect the heart against ischemia reperfusion injury. Now, there is a problem translating this into the actual body, and this is it. Short linear peptides of 9 amino acids or so are very unstable in body fluids. And I determined this with my friend and colleague at the veterinary school, Jia He. We looked at the stability of peptides using mass spec in isolated blood or when injected into the circulation of mice, and found that the peptides really didn't last longer than 10 minutes, which is really not sufficient to provide any type of therapeutic effect. So this got me started thinking about how we might protect the peptides
when they were inside the body. And we tried nanoparticles, and in our hands that didn't work. And then I came across the literature on exosomes. And so exosomes are these tiny 100 nanometer wide vesicles that all cell types in the body seem to secrete or express. And it turns out they're involved in long-range signaling between cells. A cell, say, in your big toe will release one and maybe travel up to your brain even and provide some information to neural cells. So they're not like, they are involved in intercellular communication, but it's not the direct type of intercellular communication that I've been talking about with, say, the gap junction. But the pharmaceutical industry, and also me, got excited about the fact that, well, maybe they could be used to prevent the breakdown of fragile drugs such as peptides or microRNAs or antisense from breakdown inside the body. Another interesting aspect about them is that they're non-immunogenic. They've been basically designed by natural selection to fly under the immune radar, or at least some classes of them are. I'm not certain whether that's uniform across all exosomes produced by all cells, but certainly the ones I'm going to talk about in a minute are. Another beneficial aspect of them is that some classes of them show a unique ability to navigate biological boundaries, such as the blood-brain barrier, which is obviously an important biological barrier to drug treatments. So if gap junctions provide the cellular internet, we can think of exosomes kind of like the FedEx service of the cell. Now this young man here, Spencer Marsh, joined me in 2020. He's also a biomedical engineer. And the first job I gave him, I said, fix the electron microscope because we need to see these things. At 100 nanometers, they're too small to see on a light microscope, and so we needed the EM working to get a look at them. And so that's exactly what Spencer did. And Spencer's really been central to much of our work on exosomes since that time. Now, we started off isolating exosomes from cultured cells. And I remember standing in the lab with my lab manager, Jane, and looking at a tiny pellet in the bottom of a microfuge tube saying, this won't do. All this work, all this money, and all we've got there's this tiny pellet at the bottom of the tube. We don't need pellets, we need buckets of exosomes if this is going to be translated into a pharmaceutical. And so Jane went off, and a few days later she came back and she said, milk seems to have a lot of them. And I said, oh, that's interesting, let's take a look at that. And as we read more, we learnt that another fantastically useful aspect of milk exosomes is that, of course, they're designed to be ingested. They're all about passing information from mother to baby. Again, not all exosomes can be consumed orally and then become bioavailable within the body, but milk exosomes can. So our first problem was to figure out a way to isolate them, and we had to solve a number of problems, this being the first one. You can see here these vesicles within this EM preparation, and you'll notice if you look closely that almost every one of them is intimately associated with these strands of proteins. So exosomes just don't float around in milk like a little space capsule. They're actually attached to a matrix-like complex of proteins, many of which comprise caseins. So in order to get them, we have to free them from this association. And one of the first ways that we did that was to use EDTA to break up the casein micelles. We subsequently developed other methods, including using the amino acid tryptophan, which seems to cause dissociation of the exosomes from the strands of protein. And that has the benefit that it's less toxic than EDTA in the production of the EVs. The other problem we had to solve was, and as I mentioned, I was very interested in being able to scale the isolation of the exosomes. And most exosomal isolation protocols that were available as we started into this are based around ultracentrifugation. And here you can only do 100 ml batches of fluid. And so we started playing around with different filtration-based methods. I actually had a colleague from Mayo in Florida who was isolating measles virus, who alerted us to this technique, tangential flow, in the isolation of membrane-bound measles viruses, which are about the same size as exosomes. And so we incorporated this, played around with other filtration techniques, including Cepheros column separation, and eventually through a lot of failure, we arrived at the point where we were getting these ultra-dense concentrates of exosomes out the other end. Now, the International Society of Extracellular Vesicles has pretty stringent criteria for definitions of exosomes, including the expression of exosomal markers, nanoparticle tracking analysis of their size and also their density. And we developed some protocols of ourselves. This one here was an interesting one. Here we're using esterified calcine, which is taken up and retained in the exosomes. And I'll get back to this in a second because this observation turned out to be helpful when we're trying to figure out how to get the peptide into the exosomes. Now, one of the most remarkable things was just how many exosomes were present in milk. We found that they consisted around 10 to 15% by volume of the input volume of the milk, which is just astonishing. Also, our counts using NTA revealed that there were around 10 to the 12, 10 to the 13 exosomes per mil of milk, which suggests that there's around a quadrillion exosomes in a litre of milk. And at this point, I'm going to do my clinical trial. So this is purchased from farmers. All right, on Queen Street, so I'm sure it's of the highest quality. Oh, it's got one of these caps on it. All right. I know Sherry's looking at me, my partner, and saying, he's going to spill it. I can see it coming. All right. So, excellent. I just drank 3 trillion exosomes, thereabouts. So, and I'm still standing here, so obviously they're not toxic. In fact, it's probably an absolute miracle that we're not standing around mooing at the amount of milk that humans drink. All right, moving on. Again, I put this slide up to emphasize that the numbers are astronomical. Okay, so a Kiwi connection. We were isolating exosomes in litre volumes, and that's not a litre. At lab scale, we wanted to see if we could move it up to much higher volumes of milk. And in order to do that, we reached out to Professor Richard Archer at Massey University down in Palmy. And he has a pilot plant, or he developed a pilot plant at Massey for processing dairy products. And Fonterra was very generous. They gave us a tanker of milk. And so Spencer went down there a couple of times to run huge batches of milk in sort of 300 to 500 litre batches through the pilot plant with Richard. And he returned to New Zealand with kilograms of white powder. How he got that white powder through customs is anyone's guess, but nonetheless, he did so. And I mentioned lyophilization, and this was important to us because at about the time that we were sort of getting into this, the US Biodefense organization, BARDA, we were talking to them and they were emphasizing to us that we needed to get away from cold chain storage for our exosomes. By cold chain, what they mean is storage at, say, minus 80 degrees Celsius. And the reason that they were all about that was, of course, because of COVID and COVID messenger RNA vaccines, which have to be stored at minus 80. So they were more interested in products that could be, say, stored at room temperature. So we put a lot of effort into trying to figure out how to lyophilize or freeze dry the exosomes. And in this work, I had a very talented medical student, Alan Dogan. Alan actually also is a bioengineer. Anyway, what we found was that this cryoprotectant, trehalose, in combination with this amino acid, you've heard it before in the talk, tryptophan, provided a formulation that beautifully maintained the structure and the bioactivity long term. So we've done tests. We're now up to 18 months at room temperature, and we can bring the exosomes back up in an aqueous solution, and they're still structurally intact and bioactive. Now, I mentioned drug loading. Of course, we needed to load our peptides, our C-terminal peptides, into the exosomes. And here is this dye molecule that was glowing in the glowing green in that earlier image, esterified calcine. And the way esterified calcine works is it's got ester bonded methyl groups associated with it. And when you put it on cells, it crosses the membrane because the molecule's slightly soapy, it's hydrophobic. And once inside the cells, the ester bonds are cleaved and the molecule begins to glow, but it's trapped because it's no longer hydrophobic and can't cross back out of the cell. And so when we put calcine on, I'm going backwards. Oh, there we go. When we put exosomes, calcine on our exosomes, they were beautifully stained by it, and they retained the calcine for hours. So that suggested to us that there must be pretty heavy-duty esterase activity inside the exosomes. So I said to the lab, maybe we could use this to load our peptides into the exosomes. So I contacted a colleague up at University of Virginia, Rachel Lettieri, and she and her then PhD student, Mark, started producing esterified versions of connexin 43 CT peptides. We call this peptide Act11, and when it's esterified at these 4 positions here, they correspond to aspartic acid and glutamic acid residues, as well as the C-terminus itself, Act11 for OME. So Mark took exosomes loaded with the peptide and into the mass spec and confirmed that the de-esterified peptide was in fact taken up into the exosomes. And we also used another technique. Rachel put a fluorescent tag on some preparations of our alpha-CT11 for OME, and then we tracked it using fluorescent activated vesicle sorting, which is a variant of fluorescent activated cell sorting, to measure the uptake of the dyed peptide into the exosomes. And we found that at about 100 micromole concentration of the esterified peptide, we're getting about 85 to 95% of the EV showing evidence of uptake. So we're able to produce the exosomes at scale. We're able to load our peptide, alpha-CT11, into the exosomes. The next question was, can we observe bioactivity in vivo? So to look at this, we started working with other colleagues up at UVA, Antonio Abate and Stefano Toldo. And so Stefano is expert at giving mice heart attacks. And the way he does so is to ligate the descending coronary artery for around 30 and sometimes 40 minutes, depending on the model he's doing, and then releasing this ligature, which then results in what's called reperfusion, which actually adds further injury to the ischemic injury. And so Stefano performed his surgery, and he also gave the mice a dose of around 100 microliters of Act11 loaded milk exosomes at around 0.5 milligram per kilogram. And this is what he observed. So this white stripe here is the actual infarct and a slice through the ventricles of one of the mice that are in the untreated control group. And you can see it sort of takes up around 15 to 25% of the volume of the ventricle. These are mice that received exosomes that weren't loaded with any peptide. And again, you see the infarct is about the same size as the untreated control heart. And in the case of mice receiving the exosomes with the peptide in, it's very hard to see any sign of infarcted tissue at all. And we can measure it, and what we observe is that compared to the untreated vehicle control, there's about a 60% reduction in the severity of the infarct, as measured by Stefano. And Stefano also carried out echocardiograms to measure the function of the heart, and again, he found that there was a significant improvement in function in the peptide-treated hearts. We also addressed the question of whether, there's some evidence in the literature that exosomes, unloaded exosomes, might have some benefit in preventing cardiac fibrosis. So we increased the dosage of the exosomes 5 times, and we could not find any effect of the exosomes. They had to be loaded with the peptide in order to see the effect of reducing the infarct size. Now, moreover, we found, you know, if you're going to treat a heart attack, it's really not much good to give the treatment before the heart attack, because you don't really know that the heart attack is going to occur, or just after the heart attack, because you know, when people have heart attacks, there's often a delay between the amount of time that they perceive they're having a heart attack and when they actually when the emergency services or the cardiologist gets to them to intervene. So you need a window in order to provide a beneficial treatment. And so we asked the question, how long out could we delay the treatment and still see a reduction in the severity of the infarct? And we found that a 1 hour delay really wasn't indistinguishable from giving the treatment straight away. But even at 2 hours, we found a modest reduction in the severity of the infarct when we gave the mice the treatment with this 2 hour delay. So here you can see with the 1 hour delay, we get about a 60% reduction in infarct size, similar to what we see if we give the treatment right after reperfusion. But with the 2 hour delay, we're still getting a 33% reduction in the size of the infarct. So the good news is there may be some benefit to even with delayed treatment. And Stefano also looked at the echocardiogram, and he found that function was maintained at the 1 hour delay, but not at the 2 hour delay. So we're getting reductions in the size of the infarct, but it didn't seem to be reflected in the function. Okay, so one of the ways that we think this is working is, as to the best of our knowledge, we're not aware of any other treatment that can be delayed this far out after infarction in a mouse model. And in fact, there's many examples of clinical trials in humans that have looked very promising in mice, but have shown no benefit in humans, probably due to the fact that this window is something that's so critical to get within. And one of the reasons we think that the exosomes are working well is because of the way they efficiently get to the injury. Now, this is a study that was undertaken by a group from Nebraska, by James Zemplini and his group. He used fluorescently tagged exosomes and then tracked them into the animals. And you can see he's looked at the difference between intravenous and oral gavage. And the interesting thing was that the oral gavage seemed to give a much more bioavailable biodistribution than intravenous injection, almost as if exosomes are in fact selected to be delivered orally. So we started to look at this in our injury model, and we confirmed, similar to Zemplini, that we were seeing uptake fairly efficiently into the heart at baseline. But the interesting thing was that we found that when we looked in the infarcted left ventricle, the level of uptake just went through the roof. So here's a comparison between the infarcted left ventricle compared to a remote right ventricle. And you can see that, you know, there's an obvious difference in the signal of these fluorescently tagged exosomes. Now, when myocardial infarction happens, there's an acute and sudden release of extracellular ATP, which turns out to be quite important in directing immunological attention to diseased and injured tissues. And so we wondered whether exosomes might be responsive also to this extracellular ATP. So we used an enzyme called apyrase to treat the mice in conjunction with giving them these fluorescently tagged EVs. And to our delight and surprise, we found that the increase in uptake in the infarcted myocardium basically went away when we got rid of this extracellular ATP. And we measured it in the infarction here. This is a log scale, so we're looking at sort of 10-fold steps here. You can see this sort of remarkable increase in uptake in the injured left ventricle compared to the remote right ventricle. And then this increase in uptake is abrogated by this enzyme apyrase, which reduces the extracellular ATP. And interestingly, when we looked at the surgical worms in the dermis, we found that the skin also showed an injury-related increase in uptake of the EVs that could be abrogated by apyrase treatment. So it's not just the ischemic injury, it also seems that other injury types also increase the uptake of these EVs. So basically, mum's exosomes are designed to go to where the trouble's at. And we're not quite certain what the evolutionary basis of this is. It might have something to do with infection and the targeting of infected tissues, but nonetheless, it's obviously quite useful in a drug delivery device that it's going to where the trouble's at. And we think that's part of the reason that this delayed treatment effect is so profound with our peptide. And it seems to be driven by extracellular ATP. This is a wonderful technician in my lab, Claire. She works closely with Spencer. And we decided to see if we could reduce this into a cell culture model. So we took these MDCK cells and scratch wounded them, and sure enough, we could find very dramatic increases in uptake acutely in the scratch-wounded MDCK cells that weren't seen in the unwounded cells. And again, we could knock it down with apyrase. We also tried putting ATP on unwounded cells, and that increased the uptake. But perhaps the most important experiment, we measured it here. I'll just brush over this quickly. But perhaps the most important experiment that we've performed in relation to ATP is this one, where we take exosomal concentrates, we mix them together with ATP, then we wash off the excess ATP and then put them onto the cells. And sure enough, they get the rate of uptake goes through the roof. So it looks like that the ATP directly modifies the surface of the EVs to increase their rate of uptake. So it's not as if the exosomes are sort of sniffing out where the injury is and sort of, walking towards them. They don't have the, the biology to be able to do that. But what they do seem to be able to do is when they go through a field of increased ATP, they become modified in a way that makes it more likely that they're going to get taken up by the cells in that field. And in that way, they're guided by injury and potentially disease. Yeah, I'm not certain whether I want to talk about this. I guess I should. This is the hard work of my graduate student. This is a super resolution image of some of exosomal concentrates. And we started doing some studies of whether the exosomes themselves express connexin 43. And what Rahul noticed was that, yes, indeed, some of the exosomes in our concentrates express this molecule, connexin 43. And so the next question was, okay, we're putting C-terminal peptides into exosomes. There seems to be a subpopulation of exosomes, maybe comprising somewhere between 5 to 10% of the exosomes that contain connexin 43. Could we, in fact, enrich for this connexin 43 population and use those in the kind of treatments that we're doing where we load with the peptide? And so, again, failure is big in my lab. We had a bunch of failed attempts at trying to figure out how to enrich for the connexin 43 containing exosomes. But eventually we found that if we incubated the exosomes with collagen and then pulled down those exosomes that bound to the collagen, they showed pretty profound enrichment for connexin 43. And Rahul has measured it. It's not advancing. Yeah, there we go. And he found that there's about a 25-fold increase in connexin 43 presence in these collagen-bound EVs. We also used the fluorescent activated sorting to measure it, and again, the experiment, as you can see, is not complete. We've only got 1 or 2 ends within the experiment, but it's trending in the direction that the collagen-bound EVs show increased levels of connexin 43. And in this experiment, what we're doing is we're popping the collagen-bound EVs onto our scratch wound model. And as you can see here, the total population of exosomes do increase significantly the rate of closure. But if we add the collagen-bound EVs, we get a step up in closure. So there's a suggestion that there is indeed enhanced bioactivity within these EVs that's consistent with the presence of connexin 43. Okay, so I'm going to close out talking about our work on radiation and cancer. I'm going to come back to Gautam, and I'll give Gautam credit here because he intuited that radiation injury might be one of the most interesting and responsive injuries to these C-terminal peptides. So in his studies, we're talking about the alpha-CT1 peptide, which is applied topically. And so together with Carissa James, who was a former graduate student in our program at Virginia Tech, she joined Zequel Bio, they developed a pig model of radiation burn injury. And in the study of 8 pigs, they found that indeed topical treatment of radiation burns with this peptide resulted in a pretty striking decrease in the severity of the burns to radiation. So again, this got me thinking, and I wondered, radiation side effects are an important aspect of radiation therapy. Of course, radiation therapy is one of the main tools used by oncologists. Around 50% of cancer patients will be prescribed it, but many patients don't even complete their therapy due to side effects. And in fact, we had last night in the cardiac bioelectricity talk, we had Professor Jackie Allenson in the audience, the head of surgery here, and she treats head and neck patients every week and sees these kind of radiation effects. So the question was, could we develop our exosomal therapeutic to address the unmet need of protecting them from protecting internal organs such as the brain, the gut, and the lungs from exposure to radiation during radiation therapy. There's also another aspect to this, which is a military strategic consideration. In the case of a nuclear attack or a nuclear accident, we actually have nothing, or no therapeutics that, well, I guess there are therapeutics that protect against mild doses of radiation, but only bone marrow. But we don't have anything that gives whole body protection against radiation injury. So this is also another unmet need. So to look at this dual need, both for radiation therapy but also as a military medical countermeasure, we initiated a collaboration with a radiation oncologist at our veterinary school, Electra Athanasiadi. And so what we did was we gave groups of mice lethal exposures to radiation, in this case a 14 Gray exposure. And what this Kaplan-Meier curve shows is that in the control groups, the untreated group, animals receiving unloaded exosomes or animals receiving peptide that was unprotected by exosomes, unfortunately for those poor animals, they all passed away by 7 days after exposure to lethal radiation. But the animals that received the Act11-loaded exosomes showed a remarkable increase in survival. 42% of those animals survived. Moreover, we could actually give the dose, in this case the dose was given 1 hour after the lethal radiation, but if we delayed the dosing with the peptide, we're still able to get significant improvement in the survival of the mice after exposure to this very high dose of radiation. We also looked at radiation-sensitive tissues, and in particular the gut and bone marrow. So here's what happens in the irradiated animals just around the time of their expiration. You can see the gut is very severely disrupted. The wall of the gut is thinned, and there's almost a complete loss of the microvilli that are responsible for absorption in the gut. This is compared to animals that received the therapeutic either 1 hour after the radiation or 24 hours after the radiation, where there seems to be quite nice preservation of the structure of the gut. Similarly with the bone marrow, there's a complete loss in the control groups in this radiation control animal. But within and this is actually the head of the femur, but within the head of the femur of animals that received the exosomal therapeutic, you can see that at 30 days there's quite nice preservation of their bone marrow. And we gave the slides blinded to a veterinary pathologist, and what she reported to us was that the 1 hour post and 1 hour, that's 24-hour post and 1 hour post treatments were not distinguishable histologically when she looked at the gut tissues from the non-irradiated controls. So that experiment was carried out in my lab. And you know, as we all know, working in the biological sciences, we have this issue called the reproducibility crisis. And so we were forced to address this by handing off our experiment to another organisation. When I say forced, I meant we actually were generously funded by the Redgates Foundation, who gave us money to carry out a clinical trial. And the mechanism we used to carry out that clinical trial was through the FDA animal rule. Around June in 2024, Spencer and I had a meeting with the FDA, and we told them that you know, we had this treatment for lethal radiation and that we wanted to enter the animal rule path. And so they said, yes, we'll green light it, but you have to do 2 animal species, you have to do toxicology studies, and you also have to do a safety study in non-irradiated healthy humans. And so via the Redgates, the generosity of the Redgates Foundation, we've been able to carry out this clinical program. So we prepared the therapeutic, the exosomal therapeutic, and sent it to Lovelace Biomedical, who, with the contract research organisation, we contracted to undertake the work. And I have to say that this was a very nervous couple of weeks for me, because you know, I made a real pain of myself in the lab. I was very worried about the quality of the exosomal therapeutic and whether we were going to mess it up or not. You know, cows being seasonal animals, you know, they may produce lower numbers of exosomes during the summer when it's hot and so on. Anyway, it was a time of great worry. Fortunately, and unfortunately also for us, Lovelace also did introduce problems into the experiment, because when we got the results back, they basically confirmed what we were seeing. And just to tell you a little bit about the study, it was a blinded, randomised trial. It was dose ranging, which meant that we had about 6 doses around the standard dose we use, 0.5 milligram per kilogram. It was versus a vehicle and a non-loaded EV control. They used a slightly lower dose. They used a lower dose of radiation, 7 gray, as opposed to the 14 gray that we used. And they calibrated this dose in studies of thousands of mice to determine that it results in about 70% lethality over the 30-day period of the study. There were 20 animals per group, balanced for males and females, and each of them received an oral gavage of the dosage that they received. We were very happy to see that our standard dose, which is the one that's indicated in 1 here, as well as doses that were less than the standard dose, resulted in highly significant reductions in lethality. In fact, this 0.2 dose here, we only lost one of the 19 mice. A lone female died, so there was almost 100% increase in the survival of these animals over the period of the study, which we understand is almost unheard of. So we were very pleased with the results. So again, with the generosity of the Redgates Foundation, we're continuing these studies. We'll be carrying out a phase 1b study, looking at different dosing and timings. And then early next year, we'll be moving on with Lovelace to carry out studies in pigs with the optimized dosage and regimen. So associated with this, and this is my last slide, thank you everyone for being so patient. I know it can be a long night. In association with this technology, I formed another startup company with Spencer and also my brother Alan, who's based in New Zealand but has a lot of business experience, called the Tiny Cargo Company. The Tiny Cargo Company is seeing to the clinical and commercial development of this exosomal therapeutic. And we have just rented a 10,000 square foot space in Roanoke, Virginia, and we are having clean room, and we're assembling a clean room with the processing equipment necessary for producing pharma grade therapeutic for these FDA mandated clinical trials. And I have to say, the accounting skills of my wife have been also absolutely essential to this venture. She has been, she's a wonderful part-time chief financial officer for the company. So that's it. Again, I just want to express my gratitude to the laboratory and to my collaborators, also to my funders. I'm fortunate to have an R35 NIH R35 grant from the National Heart, Lung and Blood Institute, and receive wonderful support from the Freyland family and the Redgates Foundation. Again, I want to say thanks so much to the AMRF for this opportunity to talk about my work, and also the Ted and Molly Medical Travel Fund for the underpinning of the travel. So thank you, and happy to answer any questions if you have any.
We've still got quite a bit of milk to drink.
Do you want to take part in a clinical trial?
Is it safe? So, do we have any questions for Robert, please? Julian?
Where to start? Tour de force, Rob. Congratulations. Really wonderful to see how the work has progressed to a massive factory. But I want to come back to the mice that you were looking at originally with this peptide and the heart and the fantastic effects you were seeing structurally, at least. Mm-hmm. But what caught my attention, because I was getting really excited, and then you very quickly mentioned it, and I lost a bit of excitement, which was the function.
Right.
I think you said that the function of the hearts didn't change that much, but that structurally, things repaired beautifully. What's the... am I right in saying that?
Yeah, we in that particular study, we didn't pay a lot of attention to the area, the area of the infarct. The main tool we used was to look at to use these tiny plastic bags and the pressure transducer to measure the contractility of the heart. I did have Jenny try and do some TTC staining to do live dead assays on the heart, but they were a bit of a mess. The type of infarction you get when you induce global ischemia on an isolated heart looks completely different and is much harder to measure than when you're looking at a localized infarct that results from tying off a coronary artery. And so we tried, but we abandoned those structural analyses and just stuck with the functional assay of the heart.
So did you get some sort of echocardiography?
In the in vivo studies, yes. Yeah.
Did
So
they show improvement in ejection fraction?
yes, they did. So those studies were carried out by Stefano, and so he had the mice up at UVA, and the mice were looked at. So that the experiments that returned positive signal were the treatments where the exosomes loaded with the peptide were given before the infarction or just after the infarction, or with the 1 hour delay. The 2 hour delay, we didn't see an improvement in left ventricular function. So, yeah.
Thank you.
Yeah, fantastic talk. I was interested about the animal rule FDA. How long's that been around for? Because that's great to see that they're doing that.
You know, I don't know. When I was giving Gourdie credit, the way he found out about it, because he used the animal rule as part of his pathway for the radiation burn study, was there was a guy, and this is going to be a bit like a Shaggy Dog story, but there was a guy on the Technology Transfer Board of Virginia Tech, a guy called Paul Waymack, and he was an ex-commissioner at the FDA, and I met him, and so I called Gourdie and I said, you need to talk to this guy because he knows his stuff about the FDA, and Gourdie talked to him and got on with him, and then through that relationship, he found out about the FDA's animal rule pathway, and so that's. But you know how long it's been in place, I don't know. But you know, of course, once he learned about it, then you know, I knew about it, and so that's what we took advantage of with the experiments I just talked about.
Yeah, just for the people online. Thanks, Reece.
Okay, I'm going to ask a naive question, maybe embarrassingly.
That's
so.
all right.
When you were speaking about the first rodent study with the hearts, you said something like, well, you can't give this treatment before the heart attack, of course, but one of my thoughts was something like, why not? In the sense of, does this treatment, is it plausible for it to be preventative in some way, such that if I took some pill every day for the rest of my life?
Or maybe drunk unpasteurized milk.
Yeah. Something like
because
that.
it's stable, I was thinking along those lines, you could just have it in the ambulance, because the ambulance would be good at knowing someone's got a heart attack, right?
Yeah.
So my neighbour actually had a heart attack, and he was in Helenswood, which is about a 45-minute drive, and then 2 hours got stented. But I can imagine if the ambulance had something like that, and I drive out, get the water, shake it up, and drink this.
Yeah.
Well, you know, I give my kids a vitamin pill every day. If I were to take one of these every day, it seems kind of...
Yeah, so on your question though, it's Reece, right?
Yeah.
Yeah, I mean, it's, so, you know, you're thinking something prophylactic and maybe taken every day. Yeah, we don't know. You know, I was chatting with, so I had lunch with Colin yesterday, Colin Green, my old boss, and he's always such fun to talk to. And he was talking about, you know, the way that these interventions that target connexin 43 work. And he is all about the acute single treatment being the thing which provides the most efficacy. So, you know, he had some sort of anecdotal observations that supported the thinking. But the truth is, you know, we've never really looked at the effect of chronic repeated dosing. And it's something that we, you know, really should do because it, you know, could provide us a pathway to, you know, addressing issues like heart failure, for example. So not just prophylaxis, but, you know, also, you know, frank disease of the heart. But yeah, I think it's a good question.
What's been really interesting too, I think, across both the talks tonight, it's really evident how crucial the networks and relationships and collaborations are. Without those, I mean, you know, when you talk about how you'll talk to somebody and then somebody else will do some part of it, so that whole teamwork and discovery and the different minds, the great minds involved with it is just so important. So I'd like everyone to thank Professor Robert Gourdie for his amazing talk tonight. And I just want to invite Professor Donna Rose Addis down so that we can say a proper thank you to them both. And as this is the last of our sort of our more public speeches tonight, presentations, I would like to, these two have been absolutely incredible, and I don't mean only because of their research and their professionalism and what they've achieved in life, but how personable they are and how much fun kind of we've had over, you know, like it's been a pretty solid last 3 days, but they've gone over and beyond where they needed to, and we were so fortunate to have two people of this calibre come back to New Zealand to help us celebrate our 70th anniversary. So on that note, I would like to, let me just see which one's which, because there is a colour difference, knowing the colour preferences.
Is it blue?
There we go, hang on, we'll give you that one.
Thank you.
Robert, thank you so much.
Thank you, Sue.
It's been a real privilege and pleasure. Thank you so much. And that's for you. There we go. And
yeah. Thank you as well. Thank you, Sue.
Yeah.
I can't wait to open it.
You can open it when you want. But so that wraps up our formal part of the night. They both have busy days tomorrow, loaded up by us again. But on behalf of us all, thank you so much. And good night, everybody. We just want to